Okay, Mr. Iñez, you have 10 minutes now. Go on, please.
Good morning, everyone. I am Jose Iñiguez. I am going to talk about implement the final element method to analyze structures composed by means in the plane. Well, the objective of this project is to analyze a ship's frame using a program with the Python programming language applying finite element. So we have the next agenda: design process, discretize, programming, analyze results, and conclusion. Process design. The first step is very important because here you can model from the easiest condition to the worst condition that will be shown after. The second step is to determine the equivalent force in each joint. The third step is run the program and check the results, and the last one is saves data for all elements and go ahead analyzing the next case for discretize. I worked with 4 cases that you can see in the figure. The W bottom was considered as a solid floor. In the first case, I worked with 7 joints and arrived at 3.4 meters. In the second case, I have 13 joints and the same draft. And the third case is I worked with 70 joints, the same draft. And the last case is I work in the worst condition of navigation. In the last case was when the freeboard is reduced 76 millimeters of this from the deck line. This is known the marginal line. In all this case, we take advantage of the symmetry of the structure, which was considered clamped on the joints and the certain line and the beginning of the frame due to the solid floor. Programming. That you can see the flow chart on the left. This program was divided in 3 important parts. The first part is information and system metrics. Well, the first thing that I do in the program is import the libraries and consequently proceed to extract all the information for each element of the structure. The program will read a document called project FEM that you can see the title, which in a list will have the geometry data as angle, length, area, inertia, and another list the condition, the force and moment of each joint will be saved. And it will work with the different values from the database. It calculates the easy local K matrix. Having done this for each element, the next step is build the global large matrix. The second part is boundary condition and stress calculation. Now the program solves it with learning in class, and the right of the force and displacement are filled with the results. Once the internal force distribution is calculated, we obtain the bending moment distribution for each element. So the last one is the result file, and then the program creates a text file with the result for each joint and respective safety factor for each element. I will present the results that we're determining in different case. This is the first case that you can observe in the result stress for each element with the safety factor. The third case is we have the accurate result that because I work with more joints, that you can see a good safety factor and the stress for each element. And apparently, you can say the well-designed structure, but the last case is the more interesting because the structure is the strange situation that you can see that that we have a greater stress and the safety factor is almost zero. And analysis of result. Here I made a graph of displacement of frame in X and Y that you can see how the result converges according to how the number of joints that you can see the case 17 joints is almost similar the 30 joints. And conclusion, the final element method allows us to analyze any type of problem in a naval structure, no matter how complex it may be, isolating and observing its particular behavior. It allows us to address the problem in different conditions, obtaining values with accuracy impossible to achieve otherwise. From the converse graph, it was observed that by increasing the number of joints, the results begin to converge to a single value, concluding that discretization is a fundamental step to obtain more accurate results. The last conclusion, this structure was analyzed in the worst condition when the raft is at the same height as the marginal line. I conclude that the structure was not designed to withstand the beam in this condition in the mesh. And the recommendation before starting any type of analysis is vitally important to make a detailed study with modeling entails to take into account the strange situation in which the structure can be found, since the objective of the final elements is to facilitate the task of design. Thank you.
Thank you very much. Good presentation. Just one question. It's about the permissible deflection of the structure. Let's suppose that you require the maximum deflection to be a certain value, say 1 or 2 millimeters. How would you implement this calculation in your structure? So the structure can tell you the maximum that this value has or has not been exceeded. How can you implement that in your code?
How implement the maximum?
No. If the allowable deflection has been exceeded or not. See, for example, let's suppose that the maximum deflection that I can allow in this structure is 1 millimeter. Okay.
Okay.
How can you implement this calculation?
I can put the program.
Where? In what part of the program?
O sea, I can put in the program the limit of the displacement.
Yeah, but where can you? I mean, I can read the maximum value, but the thing is that how can I know that this maximum value is exceeded or not? In what, for example, can you show me your code, and can you show me, for example, the place when you calculate the deflections?
The code?
The code, yes. And can you show me the place in the program, in your code, when you calculate the deflections?
One moment, please.
Sure, sure.
Yeah.
Okay.
Yeah, you can see.
Yeah, I can see. Can you show me where you calculate the deflections?
The friction
of the structure. Yeah.
Yeah. And this is a for the stress condition and
No, show me. We don't have the time to show all the code. I want you to tell me where you calculate the displacements of the structure.
Yeah. This is the convert the local.
Yeah, but where you calculate the displacements in general?
Here.
No. This is converting the global to local. I want to see where you calculate the global displacements. No. Remember, you have to, when you solve for the global displacements, you solve for the whole system of equations. In that point, you calculate the displacements.
Yeah, okay. Yeah, this part is when you put the information of each joint, right? That is we put the big values to convert this metric, right? And then you and then you calculate for the inverse matrix, and this part is where the found the local displacement and to transform it the
and you calculate the global displacement there.
Yeah.
Okay.
And to calculate the global displacement, right?
Yeah. Okay. That's enough. Thank you very much. Thank you very much for your presentation.
Sorry for my listening. I don't.
No. You don't have to say sorry. We don't have to say sorry. We're just working. Okay, thank you. Thank you for your presentation. Isaac, would you please allow the next group to come in?
Okay.
I leave the meeting, right?
Yeah.
Thank you.
If you want, you're going to stay, but you cannot say anything at all. There's no problem for me. This is not a secret.
Morning, doctor.
Good morning.
Good morning, doctor.
So you're Pincay, and Sanchez is here. Is Sanchez here?
Yes, it's here.
Would you please turn on your cameras and be ready because
Morning, doctor.
good morning. Okay, you can share the screen now.
Okay.
And you tell me when you're ready. Are you ready?
Give me a second, doctor.
Sure. You tell me.
Okay. Yes, we're ready.
Okay, go on.
Okay, good morning, doctor. Engineer Isaac. Today we were going to explain what we did in this project of finite element method beam analysis in the plane. We are group number 8.
Yes.
This is the agenda for today. First, we will explain an introduction and the main objective to achieve this project. Then we will talk about the discretization and the necessary information that we require to complete this project. Then we will explain some of the programming and the general procedure we follow to achieve this. Then we will show you the results we got. Then we will explain the analysis for these results. And finally, we will have some conclusions and recommendations. So this is the frame that we were assigned to analyze. This is the B45 frame. As you can see, these are the main characteristics that we needed to analyze it. We were given a draft of 3 meters and a spacing between frames of 2.28 meters. About the discretization, as you can see here, we got 15 elements and 15 joints. This is the more accurate discretization we had. We did it from above midship to, from above the double deck to the double bottom to the deck. And as you can see, in the center line is the origin of the global reference system. And in the red numbers are the elements, the joints, and the blue ones are the elements. So this is the information that we needed to fill the TXT file for the program. This information was for every element. So in the first place, we needed the number of this element, then the X and Y points for each joint from the origin. We will explain later why. Then the area for each section, and the jump modulus that was the same for every element because it was steel. And then the joint, the first and the second joint for each element, and the external forces and moments for each joint. Also, we needed the geometric boundary conditions for each joint and the sectional inertias. You can see we had 3 sections, well, 2, but 2 of them were ubicated in a different way, but was the same. And the third one that was of different dimensions. And above, you can see the external forces for each joint. There were distributed forces, so we made it punctual, following the chapter 3. And this is a general visualization of the TXT file.
For the programming and general procedures, we have the take the read information from the TXT and convert, transform the information to the dictionary for each element. Get the different metrics, get a dictionary different to the force and geometric boundary conditions. Now, then we take these values to calculate the global stiffening matrix and get the main diagonal from the and change the value. We have the 0 to avoid and get the singular matrix. For that, then we have the inverse matrix and get the displacement for the global reference system. And then to convert these values from this vector to the displacement to local reference system for each element. Next. For this, the main function, the source code, we have the correct dictionaries. In the same case, the number of the elements for each one to get a relationship and the calculate and transform the values. Using the NumPy function main to make easier the calculate, for example, lignab to calculate the inverse of dot to the multiply both metrics, metrics and vector. Plug the functions to show the static structure, and then compare the deformation for each joint and X and Y direction. Next. We use these metrics from the Logan book to get the stiffening metric for each element. Then for the result, we have the TXT, the file when we have for each element displacement in one node, join 1, join 2, and the normal stress for the local reference system. Then we have the force in the direction for the local reference system. Then finally, we have the plot, the result when we have the static equilibrium, the frame, and the deformation knowledge like it's moving, right? Upward or downward. We have to compare it. Thank you.
Yeah. On analysis of results, we choose the structure with a 15 discretization because it's more because it have more precisions for calculus. Okay, as we can see on main deck, element have the greatest deformation that we can see on node 14. That is an 6.2 centimeters of displacement in that point. And at element 12, that is the diagonal element that this reinforcement have the greatest force in magnitude because of the more distributed force on the deck. The deformations near the water line that is below the node 4 are low because they contrast each other. This, on conclusions, on recommendations, we have that design of this structure are able to start a construction because they won't fail because of the properties. The hydrostatic pressure contrast that we say at the beginning, the effect of the deflection of the structure. the maximum value of normal stretch in the reinforcement below the main deck, we find this value, that is the reinforcement diagonal behind the main deck. The Python programming facilitates the long calculus process because they help us to make this operation like multiplication or inverse, and for a lot of numbers of matrices. As recommendation, we have to follow an order for the TXT information input, because we have to take care the nodes or in X and Y direction. It's important to differentiate the type of the section that we are going to analyze, because they have different properties, because they can be flat bars or T form bars. And the last recommendation that we have is, if we have more amount of joints, the precision, it will be better, because we analyze with a more precision. Thank you, Doctor.
Now, if we can, let me show the program results. Let me share the screen, Walter. Okay. I can't. Okay. Well, here we have the result for the show the program. We get the frame.
Mm-hmm.
Here we can see the move, the joint displacement. When we have degree, when we have one is deformate. For each joint, we can appreciate these results.
Can you explain me in the program where this part of the code is being implemented?
For this part,
yes, for the graphics.
Yes. First, we have these parts. For each elements, we can create the dictionary, the points, mechanic characteristics. Yes, it get this different metrics. Then we get this. We can do simple arrangement for X and Y. Can plot these values and X and Y. It can show them align from joint 1 to joint 2, or joint A or joint G to create this.
Okay.
The color of the line is very, we got the line. This value is the thickness of the line for this.
Okay.
For this part, we have the point red.
So that's the color. Okay. Yeah.
Yes.
Okay. Okay. Good. That's a nice program.
Yeah. This program is for H1, the friends. Included, we take the example from the program book, get the same results.
Okay, let me go to, because I need to go on. Mr. Sanchez, can you show me in the program how you calculate the distribution of the bending moment? Mr. Sanchez, can you show me?
Okay, Doctor.
In the program, can you show me how you calculate the distribution of the bending moment?
Yes, yes. As my partner says, we have to in Spanish is recorrer all the data that we save on dictionaries, and there we can make the right there. We have to recreate, okay, because in the TXT we have we extract all the data and save it in a dictionary. And then this dictionary, yes, then this dictionary of all the extract data that we have to calculate the bending moment, we in Spanish is recorrer.
But in the program, where do you calculate the bending moment? That's what I would like to see in your program. Where do you calculate the bending moment? That's what I want to see, that you explain to me.
Yes. Can you help me, Gilson, because
yes, we use directly the different metrics in
right there. Yes.
Friends. Here we include the effects to the part.
No. My question is, where do you calculate the bending moment, Mr. Sanchez? Where do you calculate the bending moment? The bending moment, that's what I'm interested.
Okay. Here.
Yes. Can you? Yeah. Yes. And that I say you, doctor. Here we are. All the properties are there, and we extract on the TXT all the information, and we save it in a dictionary, and we choose the position and multiply and make, yes, right there where my partner is showing, and we use all the properties. We multiply that value for each position on the dictionary, and we use this code of NumPy around and make this process to calculate these moments, and we all save it in another dictionary that is the results.
Okay, that's enough. That's
Okay.
enough.
Okay.
Miss Pincay, can you hear me?
Yes, doctor.
What commands did you use to solve the global system of equations?
Okay, can you put the global matrix, please? Yes.
Yeah. Here we have the global.
We define a zero matrix. We fill a matrix with 0 values, and then we use the help of the dictionaries, the different dictionaries that we define, because this facilitates the organization of each characteristic for each element. So then for this, we use the formulation that you said in class, that Ordóñez said. Mm-hmm. And that's how we got the positions for each joint, for each element, and we started to fill the 0 matrix.
But my question is, where do you calculate for the displacements? And my question is, what commands did you use to solve it?
The displacements.
The displacement, yes.
Oh yeah, the displacements here.
This is a local displacement. I'm talking about the solution of the system.
After the inverse.
Exactly.
After the inverse.
After the inverse.
We get the lowest different matrix, then the back value matrix. Then we have the inverse. Then we get the inverse.
Thank you. That's enough. Okay. Okay. Thank you very much. Isaac, would you please let the next group in?
It's enough, doctor. We can update.
Yeah, you can go. You can go. Or if you want, you can stay, but I have to keep you in silence.
Okay. Thank you, doctor.
No problem.
Thank you, doctor.
Good work. I like it.
Thank you, doctor.
Okay.
Doctor, good morning.
Good morning. You can share the screen, people, group 10, Carrillo, Carrillo, Wacon, and Cano.
Luis Cano. Okay.
You tell me when you're ready.
Okay, doctor.
You ready?
Cano?
Yes.
Are you ready? Are you ready?
Okay.
Okay, go on.
Un momento. Good morning. We are group 10. Me llamo Luis Carrillo, Eric Wacon, and me, Jose Cano. In this presentation, we will talk about the analysis of a frame by finite element method. Next. The agenda for this presentation is project objective, introduction, frame analysis, results, analysis of results, and conclusion and recommendation. The objective of this project is design and implement a Python program executing the FEM to analyze a structural frame of a chip, which will be composed of being in the plane. Next. The finite element method is a numerical technique for finding approximate solution to boundary values problem for partial different equation in simple terms. FEM is a method for diving up a very complicated problem into small elements that can be solved in relation to each other. Next. A frame element is formulated to model a strike bar of an arbitrary cross-section, which can deform not only in the actual direction, but also in the direction perpendicular to the axis of the bar. The bar can carry both axial and transverse force, as well as moment. Next.
The result we made analytically by Excel experimentally with Python with two description of 20 and 23 elements. Next ideas. For the analytical result with Excel fields and table, it was necessary the areas inertial, angle, length, and sectional model, and to be able to obtain the matrix of each element and then obtain a global matrix. Already obtaining the initial condition of force and moment of the structure, we find the displacement matrix that the Excel gives, used as a result of the stress for each element, and the moment as well give use local displacement and check if or maximal stress in within the DNV range. Already obtained the result in Excel we use then the compare with our Python program. To obtain the result in Python, we need two txt, which the fields contain the characters for each element, and the second with the initial condition. Also, the matrix library will use from dictionary list. We also use the function of if, else, and for. The program gives us a result txt which indicated the force of each element, the stress, and the moment also determined if it was tension or compression. Finally, the indicated the maximum and the minimum stress, and if the maximum stress was within the lower by DMB. Next. We have a summary table where we make a comparison of the analytical method and the other using Python, checking as a reference the deformation force and moment, and we verify that the error do not exceed 1%. Next. In both table, we have the result of the global displacement with 17 and 20. We also take a variable, the experiment that is the same from the entire whole for both cases in order to obtain a coordinated of point and have a function that will be explained below. Next.
Good. Take me is about the analysis of the result. Analyze result. Remember, we have two different discrete sets. For example, I have the first illustration. You can show where it is. I have the 70 joints and the other 20 joints. Sorry. Yeah, good is about the difference. Is implement. You have. I can need in for case the field I can do it in Excel and implement the element infinite method to necessary to guide in the program Python. Good. I have this solution is how the this is analyze the distribution global for we respect the joints and the stress we respect the joints. You can show where this have the date illustration is incorrect, difficult. Next, they change the axis in X, the joints for perimeters for joints or element. You can show what is the best illustration. It's very good, it's similar. I need, it is about all the system, from the structure shift, the stress and the displacement. Remember, we have the analyze and the soon only the whole the ship, the from the ship. The whole, sorry. I have the, for example, I have the perimeter. The maximum value is 0.0025 meters. It's good, very less, very small, sorry. I have the, you can show it, the different section, the bottom, a bulkhead, double bottom, and twin deck, and main deck. I can show where this is value, the deflation is approximate 0. Good. I have the do have the different displacement, the different joints. Have the only deck. For example, the 17 joint at 13 joints. Good. I have the analyze size, only hole, the stress. I have the two fusion. I have the 20 element, fighting element. I analyze size. If we can, the maximum stress is minus 458 tons over meter square. Is the maximum value. Analyze this value is not do not exact stress maximum for the NIV. No problem. This is from a structural shift. The conclusion and recommendation. The conclusion we are about the discretion. In discretion, I implement more element or more joint. We had a more approximation at the function, different function. For example, in this case, and the placement the stress. I about is speaking is about this different section. We implement more element, more joints. We have the increment the stress because have the I implement more elements is we have less length. The stress is proportional inverse and length, no problem. You can show what this. Have the value in the whole we respect And the internal structure, for example, bulkhead, main deck, and twin deck bottom. This is how the valve the deflection very less. We respect the accreditation 20 joints. About speaking, have the more high stress is in 70 element. We respect the angular reference. We respect the system local, global is 28 grade. And analysis structure conclusion, we can have the compare two programs. Is very half the percentile error 0.18 to 0.02 error is more acceptable. Is acceptable. The more implement the discrete size element or joints, you have the thesis value error is reduced. And compare the analytic, we respect the program Python. We have the percentile error is about the 0.01. It's very, the percentile error is very good. It's very good. If we can do two options, two methods, they calculate different variables. For example, in this case, the stress and displacement. My parents, it continue recommendation. Canon.
Recommendation, it is advisable to check with the inertia of the element to recognize what type of structure they are. It is recommended to make the matrix in the Excel program before the Python program. Since in Excel, it is much easier to notice an error. The matrix are better displayed. It is also advisable to look at which system of which unit will be worked on with respect to the project.
Just a second, people. It's already 12 minutes, so I have to stop you here, okay? Let me ask a couple of questions, okay? Mr. Carrillo, in your computer program, okay, how do you identify the reactions in the supports in the vector of external forces or moments? After you calculated the displacements, okay, you calculate the external forces. How do you identify the reactions in the supports?
The support, this is depends.
No. Show me your code. I want to see your code. I want to see the computer program.
The program is this is date have the implement the date to intros a program. You have the calculate the other method analytic is you can is variable is necessary. The whole is have the calculate for method energy.
No. My question is okay, in your program, I want to see your program. And in your program, I want you to show me where do you have the reactions in the supports in your program, in your computer program.
Doctor.
Yeah.
The program introduced TXT with the external force. Here.
I know the external forces, but I want to know is, okay, in the program, okay, you calculate some external forces that you do not know. And the external forces that you do not know are the reactions. I want to see where you calculate those reactions. Or how can you do it if you didn't implement that part? See, when you have an instructor, okay, the external forces are forces, some of the forces you know, pressure, weight, things like that. But in the supports, there are reactions, and you do not know the reactions, right? So you have to calculate them. where would you, or how would you calculate those reactions? That's what I want to know.
This is depend the boundary condition, doctor. For example, we have the system, the clamped and free.
But I want to see the computer program. I want to see the computer program. I want you to show me the computer program.
We think the fourth field with the analytical method and
I want to see the computer program. I want to see it. So I want you to show me, for example, in what part would you do this or would you do that? You don't have the computer program?
Yes.
Show it to me.
This is program I have my parents work on.
yes,
Work on, you can share screen.
yes, yes, screen.
Continue, please.
Yes. The program, doctor, the program is
Okay, Wacom,
yes,
in your process, in your computer program, after calculating after solving, okay, the global equilibrium equations, what's the next step? After solving the global equilibrium equations, what's the next step?
in this part, the matrix multiply for the internal force and in replace the value, the one elevated 25. In this part is the matrix force and the displacement global.
And then what? Okay, I can see, yeah, okay. But the problem is that, so that's not a matrix force, that's a vector force, okay? But anyway, that's good. Mr. Cano, are you there? Can you listen to me?
Yes, doctor.
How can you reduce the number of lines in your program? Is there any way you can think of how can you try to reduce the size of your code?
For example, in the calculate the matrix general matrix.
Okay.
The process to calculate the general matrix is to formulate a matrix the 6 by 6 por 6. In this case, for example, the counters, the contadores, right?
The counter.
The counters in the matrix for fin the matrix. For example, 3 by 3 or see the star is 6 por 6 the matrix. You can replace this matrix for a big matrix. For example, of those matrix, I obtain one matrix. In this part, stop. Aquí.
Okay, that's a difficult question. Okay. Thank you very much. Your presentation was a little bit long, but anyway, it's adequate. Okay, let's go on. Isaac, let the next group to come in. Okay. Okay, group one, whenever you're ready, you can share the screen, please. Group one, Ortega, Larrea, Zambrano.
Good morning, doctor. Yes.
Please turn on your cameras if possible.
Okay.
And whenever you're ready, you tell me so you can share the screen.
No, Ortega.
Okay. Ortega, are you there? Ortega? You can share the screen. People, come on.
Yeah, doing it right now. Okay, a ver, okay, share screen. Share. Yeah.
Go on.
Yeah. Everything we call real is made of things that cannot be regarded as real. Niels Bohr. Good morning, doctor, and good morning, classmates. In this presentation, we're talking about themes analysis in the plane frames of a steel ship structure. The integrals of this group are Álvaro Ortega, Paul Zambrano, and Carla Larrea. Next. Previous. This is the agenda for today. Next. The introductions. The finite element method is currently a common tool used to solve different problems, computer problems. With this has been possible to effectively study the behavior of the whistle. The FEM method, the FEM is a numerical method to approximate the solutions. The objective, the general objective is to implement FEM to analyze a beams, and the other objective is the check the convergence. Next. Yeah, a step of the themes. The number one is the modeling the structure. Never to able to solve the complex structure because it's very difficult. For that, it's necessary a modeling the structure. In this case, we assume three things. The number one is the double bottom is not going to be considered because it's very rigid body. It is not a beam. The second, the structure is symmetrical. For that, only consider the halves. And the point that coincide with a certain line, we consider as clamped. And finally, the longitudinal rainforest we consider as a simplex support. Next. Discretization. Discretization consists of the transform models continuous in discrete. In this slide, you can see three different discretizations. Next. Yeah. The step 3 is the selection of the interpolation displacement function. In this case, the interpolation is cubic. The step 4 is the derivative of the Stieltjes matrix of each element and generate the general matrix, the global matrix, sorry. The step 5 is display the solution of displacement and external forces. These values or these results we are going to obtain the global reference system, but we need transform in the local reference system in order to calculate the strain and stresses. For this transformation, we use the matrix T. And finally, and the most important step is the analysis of the results. We should ask the following questions. The results make sense and is convergent enough? Thank you.
Okay. Now, for the boundary conditions, we consider midships and the end of the double bottom as clamped, as said before, where we know that the deflection and the strain are zero, the slope. For the connection between the deck and the site, also for the site and the cantilever, both are simply supported when we have no displacement. Finally, the reinforcement that we call slotas, that are the longitudinal supports, are simply supported as well. With these restrictions, we are going to know which are the values where the force is equal to 0 for our corrected force metrics. In order to apply the finite element method, we are going to transform the distributed load into equivalent forces and moments acting in the joints, using the integral from 0 to the length of the load multiplied by the interpolation polynomial of third order. Yeah, next. Okay. For uniformly distributed loads, we multiply the load by L/2 for the force, and for the moment in the first joint, we multiply by L²/12, and the other one, the second joint, is multiplied by L²/12, but with the opposite side, because the moment is going in the other direction. For variable distributed loads as the pressure exerted.
I'm not seeing your. Okay, I'm sorry. Go on. So go on. I'm sorry. Go on.
Okay. For the variable distributed loads as the pressure exerted by the wear of the hull of the ship, we know that the pressure is higher when we are deeper. So the graphic is showing that the red pressure is higher than the green one. So if we add them up, we're going to have a lower moment, but in the direction of the red one. Also, on the forces of the two different elements, we have them up and get a higher force. All this in the local reference system. Then we have to transform them to the global one using the cosine and sine matrix, and also the angle. Next one, please.
So I'm going to tell you how the code works. First of all, from the plot points of the geometry of the system, we wrote a short program that extracts all the information, call it the angles, the length of element, and the continuity of the joints for each element. And also it prints a TXT file, as you can see right in the center of the screen. It prints with all the properties of the material as well. Yeah, and then with this TXT file atop the limited text, it is needed to work with the big code that we made. So with all of this information, the program calculates calculates all the global matrix and it prints the results. We decided to print the actual results in a TXT file because its simplicity, depending on the number of joints or elements, to visualize the information. As we can see here, it prints the strain for every element, the normal stress, the internal force, actual force developed by the element, then the direction of the force, if it's in tension or compression, and the status, if it's safe, if the element develops normal stress lower than a security factor of the yield point of the steel. But with the Y and rotations results, we decided to print it in a more visual way because we have for every element 100 points. So I decided to do an intensity plot. As you can see here, the deflections and the strain, and this led us to the results. Oh, sorry. Yeah, okay. So as we can see here, we print the visual results because it's complexity. And we noticed one very, very interesting behavior. Can you see the black triangles here? They are SLORAs, longitudinal reinforcements. And we noticed that the higher developed stress are very, very close to those elements because it could be due to the curvature, but we are going to analyze that in the next to it. And we can see the deflections, which is as we have 100 points per element, it's kind of exact, and it's a very good, nice to visualize the information, I think. Next.
Yeah.
As can be seen in the deflection plots for the 15, 30, and 49 elements, the larger the number of elements, the larger the deflection is, especially in the zones where the maximum and minimum values can be found. This could be because the larger the number of elements, the shorter the element is. So the more exact the solution we get until we approach the analytic solution. Next. As conclusion, the error decreases as the number of the element increases. If an element is close to a strong reinforcement, this will fail if the supported load is too high. As we increase the number of partitions, the effective breadth tends to behave as it should be, increasing the probability of failure by normal stress. And it is important to analyze the entire section and not only the half of the system by symmetry. Assumptions may lead to error.
Yeah, and one final recommendation is that for a better discretization, it's better to create not only more points between one element, but to create more points following the curvature of the profile of the system, because it's very different to create more points in a straight line than just to follow the curvature. It's very different, but it's harder in terms of programming. It's a more complex program in that way. That is it. That was our presentation.
Thank you. Thank you. I like it. I like it. Ms. Larrea, there is a short question for you. Let's suppose I want to identify the rotation of joint 4, what would be its position in the global stiffness matrix? Rotation of joint 4. What would be its position in the global stiffness matrix? Ms. Larrea, are you there?
Yes, doctor. The position our is 3 minus 1 is 2, 4, no, 4 minus 1. Or, take a moment. I need a calculator. 4 minus 1 plus 3 minus 3. The position is 12.
I guess so, yeah. Okay. Okay, people. It looks to me that you did a wonderful job in your computer program. I like it really much. I'm really, but I'm surprised of the convergence results. I'm very surprised that you have such a large difference with the number of joints. The next slide, please. Yeah, that one. I'm very surprised. I'm very surprised because I would expect, for example, in going from 15 to 30 elements, that would be enough to get a very good convergence. So I would expect a very small difference between 30 and 49, but I'm surprised. And also here, Engineer Isaac, you are in trouble because your design reaches 220 newtons per millimeter square. Any comment, Isaac?
my structure is well.
Well, they're telling you that it's not. Okay, I would like to review your results and see if you can sustain. But I'm really surprised of these results. But I really enjoyed your results. Okay, people, good work. Okay, bye now.
Yeah.
Thank you, doctor.
Thank you,
Isaac,
doctor.
you're welcome. You're welcome. Engineer Isaac, will you please let the next group?
Good morning, doctor.
Good morning. You can share the screen. You can share the screen.
Sorry.
Go on. Whenever you're ready, go on.
Okay. Good morning, doctor. Engineer Isaac, this is group 11 formed by Karen Cumbe, Alex Nevares, and Bigmar Diaz. Next, please. This assignment consisted of the solve the assignment 3B using the finite element methods. Before to show the progress and results, it's necessary introducing a little concept of finite element methods. That is a method numerical for solving engineering and physical mathematical equations. Use the formulation that the matrix for solving algebraic equation. Use the first step, that's bars, and second step of beam. The first step, the bars, analyze only in direction, and the second step, analyze the force in the transversal and moment. In the case of project, combine the bars and beam elements. That's for a stiff matrix for found the result and the behavior of the H elements. The objective has the principal objective consists in analyze the structure behavior of a cross-section of the chip using the finite element methods. The secondary objective has two. Use the Python programming of the deflection, moment, stress in H element. Implement the energy method for point force and moment in aerostatic pressure or any load distribution. Next, please. The methodology used in the first, discretization, second, analysis of load distribution, three, geometric characteristic of element inertia area, four, algorithm, five, prepare the data file, one, input the force, external forces, and the other days, coded in language of Python, and finally, apply the final element methods, combination bars on beams, and obtain the results. Next, please.
Well, the discretization was the part where we divide the frames in different elements according to our needs. The first we establish where we already know we have simple supports and clamped points, clamped ends. And the only free joint we needed was here at the end of the seawater level, or the start of the seawater level, so we could employ easier math. The second discretization was made after an analysis made from the applied loads after the equivalences and forces and moments, and we saw that the main deck elements had higher forces and moments as so the most bottom of the frame. So we there put an intermediate node. The applied loads were was to change its equivalent, and the triangular was transformed into the rectangular and triangular again, because we had a trapezoid after the simple support reshaped the element. Here we got the equivalences by energy method. But we can see here from different values right from rectangular and triangular loads. The geometry was simply calculated by the dimensions of the beams we had. The only difference was the plate around it, and the shell plating was 12 millimeters and 8 millimeters in depth. This is the data we used.
Okay, good morning, Dr. Engineer Sat, partners. Okay, is the view the algorithm? The algorithm was originally created for solving exercise, one exercise, the book Dari Logan for three elements resolved 4 joints. And before I start the program code, first is necessary to identify different stage through it to reach easier understanding of it. This are made with a flowchart with the point what we need in each stage of the code. And inside each stage, they will be find the loops necessary to locate along the different build matrix. Is there in the necessary math calculate the required data for letter analysis. Here is the read text file and sort in 6 variables with elements by node, with each local fitness matrix for each element, sort boundary condition in global terms for find the displacement global letter in the displacement local. But global matrix in copy with a big value and diagonal is solve displacement, solve region, and calculate stress. The program have much libraries in resolve for method calculate various procedures the algorithm for find the matrix for each element, prepare the global matrix, inverse the matrix for find the global displacement, and later the force external. All the result is saved in our file result txt. Okay, the results we have compares the discretization high stress. This we prepared two discretization for 10 joints in 30 joints. Okay, the compare is 10 joints in 30 joints. The stress 10 joints and max stress in the joint 2 is the joint 7, and the program executes the 13 joints. We can see in the value 2 is the distribution the stress in joint 2 and 3.
Well, we got from the results, we got some conclusions and recommendations. But first, we can say that deflations don't always correspond entirely to applied loads. Why we say this? Because according to our loads, for example, we had that the same applied load was with the same magnitude and the same direction for both elements, but we could see that the deflection was one from upwards and the other from downwards. This because due to the continuity of the slope, and this piece was bigger. So this one supported more load than the other, and therefore it created a slope because there is no moment in the support, and the loads in the deck were higher than the resective pressure, and it can be seen that we need a more precise discretization because the results changed a lot drastically, Here we can compare each one of the elements or the zones, and here we can compare the highest value in all the frame with the older and the newer. It even changed sign, so it's needed a more signer discretization. And the positive is that the algorithm solved all the exercise, the first one and the second one. Recommendations, Bigmar?
The recommendation have the is be careful in the pressure electrostatic because it's no correct, it's inclined, and the superposition have be careful with when a force or moment apply is a bit confused because it's in inclined and for the analysis in external forces is necessary to decompose in the global reference system. The other recommendation is I think that it's necessary analyze the behavior of the stress and bending moment for different draft. In the case have the 3.5 meter, but what happened if the 4 meters, the 2 meters, that the stress could be dissipated more in the pressure electrostatic at the distribution. Thank you.
Okay. Okay, Mr. Diaz, if the displacement in the x direction of joint 5 would be null, would be 0, what element of the big K matrix will have to be set equal to a large number? I repeat, if the displacement in the x direction of a joint number 5 would be equal to 0, what element in the big K matrix would have to be set equal to 0? But to a large number, I'm sorry.
In the global matrix?
Yes.
Yeah. The is equal to 0 in x direction, and Doctor, I've seen that I say the force or the reaction.
No, I'm asking you. See, when you solve the system of equations, right?
Okay.
You have to consider the support conditions.
The simple support.
No. Let me ask, I'm asking Mr. Diaz right now, please. So if I want to set the displacement in the x direction of joint 5 equal to 0, then you will have to replace one element in the K matrix equal to a large number. What element would be that?
The element 5.
No, because the joint number 5, each joint has 3 degrees of freedom. Okay, let me go on. Let me go on to ask somebody else. Ms. Cumbe, let's suppose one of these elements would be a cable instead of a beam. What would you change in your data?
Which is the condition?
If an element would be a cable, what would you change in your data? Miss Cumbe. Miss Cumbe?
Yes, and change the conditions.
No. Mr. Nevares, what would you change?
Well, the cable is always in tension and it allows support. So what is the previous condition? It was a clamped.
But for example, let's suppose that just let's suppose in your model here,
okay,
on the left, for example, element 7. Right now it's a beam, and I want to convert that into a cable. What would you change?
The angle.
The cable is in element 7 or node 7?
Element 7. You changed. What would you change?
I would change. I wouldn't need to change anything because
No.
a cable allows rotation.
Exactly. If it allows, it only allows tension. That means that it cannot bend.
Yes,
so
and
it shouldn't have
just in
what?
case the orange are simple support.
No,
So
no. If you don't have bending, then you shouldn't include inertia. Okay, people, we're late. Let's go on, Mr. Engineer Isaac, please. Would you allow the next group to come in? Isaac, would you please?
Yeah, good.
Thank you. Ordóñez, Sayo, and Carrion, would you please turn on your cameras?
Good morning, doctor.
Good morning.
Morning, doctor.
Good morning. When you're ready, you can share the screen.
I'm going to share the screen, doctor. Can you see my screen?
Yeah, I can see. Go on.
Sometimes we feel that what we do is just a drop in the sea, but the sea will be less if it were missing a drop. See Calcutta. Good morning, we are the group number 2, and today we are going to present about the finite element method of beamward analysis in the plane. So the agenda for today starts with the introduction, and then the objective, procedure, results, analysis, and finally the conclusions and recommendations. What is the finite element method? Many of the times in the analysis of the structure, it's possible to find problems involving complicated geometries, complicated loadings, or complicated material properties. This is the reason that the finite element method is introduced. in order to obtain or to approximate values of a discrete number of unknowns of points in the continuum. An example of this is the frame of a ship, which is composed for a series of being elements that are connected to each other, as can be seen in the slide. The general objective of this project is to analyze the external and internal forces that are acting on the frame of a ship. And to meet this general objective, is necessary to obtain the calculate of the shear force, the bending moment, and the deflection using the finite element method. Also to compare the stress with the yield point of every beam of the structure. And finally, to analyze the results obtained in order to verify how good is our modeling of the structure. The procedure starts by calculating the equivalent force due to the hydrostatic pressure distribution. For that, we are going to use this model and also the minimum potential energy method to obtain the forces and the moments, the equivalent forces and moments in the local reference system. Then, using the following relationship, it is possible to calculate the equivalent force due to the pressure of the upper and lower deck. Since the force obtained is in the local reference system, it's necessary to obtain the inverse of the T matrix to obtain the force in the global reference system, because this system is our starting point. So this is the results of the global reference forces and moments. Summary of hydrostatic equivalent force per joint and summary of equivalent constant distribution per joint. These are the three discretizations that were used in our project. As can we see, if we increment the numbers of elements in joints, and this is because we need to obtain a convergence of the structure. So as we know, is we increase the number of elements and joints, we obtain a better results in approximations.
Now we have the flowchart of our program that we implement to analyze all of this element and this frame. And this starts with the important libraries and manually enter the name of the data sheet. This is the following all the calculations about as the flowchart said.
Well, I will explain the code in 4 different parts. The first part, with the information from the TXT file that the user gives us and the number of elements and joints, because he knows all the details. And then we can obtain the values of inertia, areas, dimension, angles with respect to the global reference system at the position with the restriction of the supports. These are the boundary conditions. In the second part, we begin to find the stiffness metrics of each element. And with the formula presented here below, joint minus 1 times 3, we proceed to placing the correct position of the global metrics. The system is also solved with the b-value method to find the displacement and reaction in each joint. Then, in the third part, we pass the global displacement to the local reference to calculate the values of stress, inertia, internal force, bending moment, and shear force for both the bar effect and B effect. At the end, we must combine both effects and compare them with the yield point. Finally, in the fourth part, we present to the user the results obtained as is the yield point pass or not to the maximum stress of the structure and in which element it is found. Also, all the information obtained for each element is written and in a TXT file. It we will see later.
Then we have the properties of the elements. As we can see, it's very important to calculate the inertia for all element of the beam, because it's very important to calculate the stiffness matrix that we can see and we can use for the global matrix. Then we have the stiffness matrix for each element. This is a little mode for, this is a part. There's other results following the stiffness matrix formula. Then we have the global matrix. Using the formulation of the joint -1/3, we have to calculate all the global matrix and positioning the elements as we can see in the slides. Then the idea is located all the results in the global matrix in order to obtain the global values of all the structures as we can see. And then the global matrix and the inverse multiplied by the boundary conditions, and we have the displacement, global displacement. And then with the global matrix, we can obtain the forces. And finally, we can obtain the values of the reactions of the structure. We also have the global at the local to the local reference and the displacement. As we can see that the matrix T, the T matrix multiplied by the DAJ global, we have the local displacement of the element 1 and the element 2. Now we have to analyze all the values obtained for other elements. As we can Daniel said in the beginning, we have 12 elements, and all the elements we have the nodes are the results for the maximum strength, the deflection, the axial force, the bending moment, and the shear force. So we can see in the table.
Well, these are the deflection graph for the force of the frame. The first, which go from the either bottom to the lower deck, present an asymmetrical deformation due to the fact that the hydrostatic pressure is not constant along this element. Frame 2, in the next slide, that goes from the lower deck and the upper deck, doesn't present an external load of the force. Therefore, these values will be very small and the curve will present some symmetry. Then, as we know, the distributed load is constant in the lower deck and the upper deck. So the deflation in this element should be constant, and they will see here in graph 3 and 4. And this is symmetric in the two graphs. It should be noted that also these values are not too large to take into account for analysis, for example. But internal force effects, such as in stress, can cause failure of the sheet frame. And we see previous.
Then we have the conversion table. And as we can see, we had a 3 discretizations of 3 trials. And as we can see in the graph, the convergence is approximated with the trial 2. As we can see in the results, that the error measured for all trials with the deflections and with the stresses. And we can see by statistics the conversion of the method. For the conclusions, after to analyze all the structure of the frame with all the elements of discretization, we have the design is not too good to express because the stress overcomes the yield points of the safety factor of 155 following the DMB rules. But then one recommendation for this is increasing the inertia of the elements of the sectional area to can avoid this behavior, and to increase the approximation, we have to choose more elements on the structure. Thank you so much. And now we're gonna run the code by our partner Ordóñez.
No. We don't have the time. We don't have the time. Let me ask you a couple of questions. Isaac, it's up to you. They're telling you that your design is incorrect. What can you say, Isaac? Just a question for you people. How do you calculate the inertia and section modulus of the frames, of the beams?
We calculate with the characteristic that the plane give us in the result, and
You don't have the details of that calculation?
Yes, I have the
Please.
table. We include in the report, but in that part in the presentation we don't.
Okay, if it's possible.
Okay,
I'm not seeing that. You're still okay.
here we have the bow section, bow structure with the table that we can see. We could see.
Yeah, I can see the plate. The plate is 228. That's meters, right? So the area is very small. Okay. It looks, Isaac, it looks like it's correct, the calculation, right?
Yes, doctor, this is correct, this one.
It looks correct. So the problem is would be, I would check. Okay. Thank you. Thank you. Let me ask a couple of questions. Ms. Sayo, could you say something about how do you calculate the big K, the global K matrix in your code?
Okay, in the code.
Yeah, how to form the big K matrix in your code.
First, if I need to share the screen, and it's not necessary.
It is necessary.
Yeah. Okay, let me see here. Okay, first, we need to the matrix K of each element, okay?
Okay.
So we have the matrix K of each element. So then we create the matrix global with the matrix, with the zero matrix, multiplying the joints that we have in this case 13. And for the 3, that is the degree of freedom, and
Thank you.
the same here.
Thank you. Thank you.
Okay.
Mr. Carrion, can you show me, can you explain me how do you calculate the P force, the axial force in each element?
Okay, let me share. Okay. Yeah, we have the code, and for the axial force, let me share. We first this is with the local values. Okay. Yeah, this is define the displacement and the stress and internal force with the global matrix. As we can see in the range of the elements, we have the displacement for each element, and then we can obtain the stresses, the strains.
Thank you. Thank you.
Yeah.
Thank you. That's enough. That's enough. That's a good question. That's good work. Okay. Okay, people. Isaac, we're going to have a break now until 9. So we have 10 minutes. So 12 minutes to take a coffee. Okay. So we will go on
we should return later or not?
No, that's enough. That's enough. Did you load your report in the SID web? Okay, yes. So that's enough. That's enough.
Thank
that's
you.
Enough. Okay.